some more Rockstar College Physics. We are going to do a problem involving the Doppler effect in sound. So it's a pretty cool problem. There's some really neat things of consideration, and let's get on with it, shall we? So here's the problem. All right, so we've got ourselves some object that's emitting a sound at a frequency of 392 hertz, which is the note G. Anyways, it is 1,000 feet away from you. Excuse me, 1,000 meters. Oh, who's using feet? So we've got this, maybe it's a car, I don't know, it's something. No, it can't be a car. It's some object, we'll just say, and it is emitting a sound that has a frequency of 392 hertz. And it begins 1,000 meters away from you. You're listening for it, right? So it's making this sound. The sound that has a frequency of 392 hertz. And we'll assume that it's already making the sound. So you hear the 392 hertz sound. Great. You say, oh, that's the note G. Great. Well, we're going to say that this object has an initial velocity that is equal to 0, but it begins to accelerate towards you. Ooh, we're going to say that A is equal to 7 meters per second squared. That way. And we want to know when. Excuse me, not when. Where is the object when you perceive a frequency of 440 hertz, which is the note A, A4. Anyways, as this object moves towards you, we got that there's a shift in its frequency due to its relative motion. And because it's accelerating, this shift keeps on shifting, it keeps on changing. So as it's accelerating towards you, it's moving towards you faster and faster, which means that as the wavefronts approach you, they get condensed smaller and smaller in terms of their wavelength, and that produces a higher and higher frequency that you perceive. Ooh, pretty neat, huh? So we want to know, where is the object? Where is the object? How far away from you is the object when you perceive this particular frequency? Oh, shoot. All right, so let's just go ahead and say, well, how are we going to approach this, right? Well, number one, we want to be able to perceive a frequency of 444 hertz. Eventually, you hear f prime is equal to 444 hertz. All right, so a good start with this would be, how fast does the object have to be moving towards you in order for that to be the case? What must V sub s be then? That's not asked, but it's something that we're going to need to figure out in order to answer the question in whole. So, how do we get this? Well, again, we got a stationary observer, a moving source, and we've got that f prime is equal to the speed of sound divided by the speed of sound minus the speed of the source multiplied by the source frequency. So there we go, Doppler shift for a stationary observer. Boom. What do we have? Well, V sub s is going to be positive or negative. That's right, we want to treat it as positive. Motion towards is positive, motion away from is negative regarding the observer and the source. The source is moving towards, so its velocity should end up being positive. That's what we're trying to figure out. But we know also the speed of sound. We're just going to assume that it's 343 meters per second. We're in air. Doesn't say anything about temperature or temperature gradients. So that's great. And we've got F here. Ultimately, what do we want to do? We want to solve this off for V sub s. So we can multiply both sides by this quantity, v minus v sub s, and sort of group things together here. So let's just do this. We've got ourselves v times f prime minus v sub f times, v sub s times f prime is equal to v times f. So there we go. We can throw this over the other side, divide by f prime, and we've got ourselves v sub s is then equal to v f prime minus v f divided by f prime. So we get ourselves what the source speed has to be such that it will produce a sound in our frame of 444 hertz. And what do we have? We've got 343 meters per second multiplied by the difference of the frequencies, 440 hertz minus 392 hertz, divided by the frequency that we're perceiving, which is 440 hertz, which gives us then the speed of the source must be equal to, we got 43 times 37.418. 37.418 meters per second. So that's how fast the source has to be moving in order to produce a sound that we will perceive as 440 hertz. All right, so we want to know where is the actual object when we perceive that sound. Tricky, tricky. All right, so let's do this. Let's figure out where the object is when it has this velocity, right? How far has the source moved in obtaining the velocity? Speed, we'll say. Speed of that 37.418 meters per second. So I answer that. So how are we going to answer that? Well, we've got a constant acceleration here. We've got linear motion. This should be pretty easy, right? We've got ourselves just some delta x, and we have a v final squared is equal to v initial squared plus 2a delta x, which we can solve out for delta x being v final squared minus v initial squared divided by 2 times a. V final is our 37.418. V initial is equal to 0. So we've got the quantity of 37.418 meters per second quantity squared divided by 2 times 7 meters per second quantity squared. Oh, excuse me, 7 meters per second squared, quantity squared. And we've got that squared divided by 14 then. Whoa, that is pretty nifty there. Ooh, we've got like 100.00859. 100.008595. Let's call it 0086 then. All right, so when the object has moved a little tiny bit over 100 meters, it will be going 37.481 meters per second, and will thus be producing the sound that we will perceive as 440 hertz. So where's the object at when we perceive it? Don't say 900 meters away from us, because that is not true. That is not true at all. By the time that we perceive the sound, this object has still moved forward, because the sound has to travel from the object, from the source, I should say, to our ear. Sound's not instantaneous. We don't hear it the instant it's producing that wavefront that correlates with the frequency of 440 hertz. It takes time for that to travel to us. So this object moves to here, we'll say that that is approximately 100 meters. Right here is when it has the 37.418 meters per second velocity, at which time it produces the wavefront. Now that wavefront has to travel to us at the rate of 343 meters per second. And in that transit time, this object continues to move forward, right? Continues to move forward. During that time. So that's easy to overlook there. Don't forget, sound takes time to travel places. Light takes time too, but locally close, it's almost instantaneous. The time it takes light to go 1,000 meters is practically instantaneous, immeasurable in terms of, hey, you want to time it out with a stopwatch? Not going to happen. Sound, however, travels at a very low rate comparatively and has significant transit times over large distances. So what is that amount of time then? Well, the distance it has to travel is, well, it's going to be 1,000 minus the 100.0086. So we've got distance, we'll just call it D, is 1,000 minus 100.0086, which will then be equal to 800.0014. Oops. 0.9914. That's how far the sound wave has to travel. It correlates with 440 hertz to reach our ear. And what else do we get with this? 1. That all seems good. So, how far forward does the object move in that time? The source will move forward by an amount given by, well, let's call it delta x2, to call it something. The distance it travels forward from that 100 meter mark is going to be equal to the time interval that it takes sound to travel to us. And then we've got equation of motion regarding constant acceleration as well. So we've got 1/2 AT squared plus VI times T. That again is characterized from where it is right there. So where is it? What's T? T is going to be equal to the time it takes the sound to travel to us. The time it takes the sound to travel to us is going to be equal to, we've got distance equals rate times time. We know the rate, we want to figure out the time. We've got the distance divided by the rate. So we've got D, the distance that has to travel to us, the sound, divided by 343 meters per second. So again, sound's got to travel this far to reach our ear from where it initially is, right there at the 100 meter mark approximately. This is going to be the amount of time, so we've got that is going to be 800.9914 meters divided by 343 meters per second. So there's the transit time for the sound. Got divided by 343. About 2.6239 seconds. 2.6239 seconds. So that's how long it takes the sound to travel to us. And the sound, the source then advances forward by some amount given by this. A, we know 7 meters per second squared. We're characterizing it moving forward from a position in which it's already moving at a rate of 37.418 meters per second. So we've got to put that all in and get ourselves that delta x2 is equal to 1/2 times 7 meters per second squared multiplied by 2.6239 seconds quantity squared plus 37.418 meters per second multiplied by 2.6239. 2.6239 seconds. Ooh, and we got delta x2 then is equal to 0.5 times 7 times the answer squared plus 37.418 times that answer. It moves forward by a distance of about 98.191. 98.191 meters. So, ultimately, where is this object relative to where it initially started? Well, we're going to have that object is at the position delta x plus delta x2 when we hear the sound having f prime is equal to 440 hertz, when we actually perceive the sound to be 440 hertz. So delta x plus delta x2 was our 100.0086 meters plus our 98.191 meters. And that just goes to a 9. We can go ahead and say we got 198.199. 199.96. Where it began, which is how far from us? Distance from us is then 1,000 meters minus 198.1996 meters gives us 802.81, we'll just call it 801, excuse me, 801.800. We can round that. One zero, boom, boom. Yep, that's good. 808.1 meters away from us. So that's it. The important thing with this is, yeah, the Doppler shift, changes in frequencies, that's cool, but also noting it takes time to travel. It takes time for sound to travel. It takes time to travel in general, right? But for sound, something that we definitely need to take into account. That's almost twice the distance that it had traveled just to produce the sound as it is for the sound to reach us. Some of that is because, well, its acceleration is pretty high, so by the time it's actually producing this sound, it's zipping. Double that, but it's going really fast. It's already going pretty fast here, right? What is that, 80 miles an hour or so? It's going much faster by the time the sound actually reaches us. All right, so that's pretty much that. In terms of using the Doppler shift expression, just make sure that you keep track. Is it going towards, going away, and plus or minus for the speeds. Have a good one. Until next, be well.